Now we start discussing the Cauchy's relation for the stress vector. So, Cauchy's relation for the stress vector reads that the traction, surface traction T acting on the surface S, that is related, linearly related with the outward unit normal drawn on that surface S. So, outward unit normal N, that is a geometric quantity, whereas the surface traction, that is a force distributed force intensity, they are related through a second order tensor, okay, which is known as the stress. Let us see. So, in order to arrive at that, verify that, what we do, we consider a small triangular block. Okay. So, chosen axis is horizontal axis is x, vertical axis is y, and this block it is a right triangular block. This point is labeled by the letter O. This point, this vertex is A and this vertex is B. Now, this block, the other faces, it is taken from a body. Say, for example, here is the body and we are taking a sample from here. Okay? We are taking a sample from here. This is the enlarged version of that. Since we have removed the other part, so these stresses they are taking care of that effect of that other surrounding effect. So, on that face, suppose Tx is acting. So, this here Tx is acting. Tx is acting. Okay? So, this Tx, you see, it can be resolved along the x-axis and the y-axis. Okay? And we assume that this AB, it is the trace of that plane which is perpendicular to the board, okay, intersecting the x-axis and y-axis at A and B point, and this line AB line is a trace of that plane on xy plane. Okay? So, we further assume that capital X axis is normal to that plane. So, this normal vector which makes an angle theta with small x axis that is normal to that plane AB. So, outward unit normal n vector, it would be having two components. The z direction is having 0 contribution. So, nx, ny and 0. So, we are solving the 2D problem, that is why the other component is not accounted. So, nx geometrically you can relate, it is basically the cos theta, cosine of theta, ny is the sine of theta. Okay? So, now we assume that okay, this Tx, the surface traction vector, it can be resolved, distributed force on AB plane, that is resolved into two components. So, we write that T x, it is having two components, T x of x, small x, T capital X of y. So, we are using the superscript capital X because it is basically the capital, it can be identified as the capital X plane. So, this traction vector is acting on that capital X plane. So, it has two components along the small x direction, that means horizontal direction and vertical direction. Now, if we consider the equilibrium of this block, what we get? We get, suppose this triangular block is having the width B. Okay? So, we say that okay, along the x axis direction, if we consider sum of all forces, that is 0, this implies that T x of x times the area over on which it is acting, A B length AB times B, and come to this face, what we get? Okay, we get sigma xx times OA times B and then you visit this face Okay, you visit this face sigma x y o b times this width b. So that must be 0. Now you see, consider the geometry, the triangle O, A and B. AB time, so this angle must be theta. So AB times cos theta is OA, AB times sin theta is OB. So we say that A length OA, that is AB times cos theta, which is AB times nx. Okay, AB times nx. Similarly, OB can be expressed as AB times sin theta, that means AB times ny. Okay, so ny. We have written the values of nx and ny. So what we get? We get T x of x minus sigma xx nx minus sigma xy ny times AB times B. Equals to 0. Okay, so we get this expression. That means, since it is different from 0, we divide this expression by this term AB, length AB times the width B, and we arrive at this expression. What is that expression? That expression, let us write it again. That expression is T x x equals to sigma xx nx plus sigma xy ny. Okay, so that we have got. Now we consider the equilibrium along the y-axis direction, y direction. So what we get? So this time Ty would be there on this face. Now when you visit this face, you get minus sign and sigma xy. Okay, and when you come to the bottom face, what you get? You get sigma yy. So that simply you get this expression y. So xy OA, OA bnx, sigma xy, and here y. Okay, and same, using the same philosophy, what we get? We write down, we get the second expression. That means T x of y, that equals to sigma xy nx plus sigma yy ny. Okay, so that means we can write this in compact manner. Okay, so we get this expression. Okay, this is basically the same representation. Here we have written the rows separately. Here we are writing in a compact manner following this statement. So this is the compact notation. We are not expanding the entries, expanding these vectors or the tensors. So entries are not visible, but here you can see the entries. Okay, So, the for 2D it is done. Now, it is time to consider the 3-dimensional one, 3-dimensional situation. Okay, coming to the 3-dimensional situation, this time we are taking a tetrahedron. Okay, so we are labeling the vertices A, B, C, and this point is O, which is not visible. Okay, this is O. So it has 1, 2, 3, 4 faces. So the face ABC, that face is that plane. On that x-axis, capital X-axis becomes the normal. Okay, so we say that we choose the normal direction to denote the capital X-axis. Okay, so that means the traction vector which is acting on the face ABC, that is identified with this T traction vector with a superscript capital X. Okay, so this capital X, this traction can be further resolved into Cartesian components, Tx of small x, this direction, Tx of y, that means y direction, and Tx of z, that is acting on the vertical direction. Okay, so in order to avoid this, otherwise it would be clumsy, I have separated these faces. Okay, this face I have drawn it here, and I have shown what are the stresses that are acting on that face. Same thing I did for this plane, that is negative y plane and negative z plane. Okay, now if we consider the equilibrium of this block, so what we get? We get, okay, we write sum of all forces equals to 0. So this time x is here. Okay, so along the x-axis is positive. That implies that T x of x times the area A, B, C. Okay, area ABC. Area ABC. Okay, so that is the force acting on the face ABC. Okay, so now we visit the negative x plane first. Negative x plane, we see that sigma xx is acting, but the direction is opposite. Okay, sigma xx times the area OAC. Sigma the area OAC. Okay, now we visit the negative y plane and we see minus sigma, this is, let us say, xy times the area OBA. OAC, OB. Okay, so that this force sigma xy is acting on the negative y plane, and along the x direction it has this much of contribution. Okay, this much force it is offering. Now we visit this negative z plane. So what we see that, okay, along the x-axis direction sigma xz is acting. Okay, so I am using the complementary condition, the symmetry of stress xz times area OCB, that must be 0. Okay, this must be 0. Now exploiting this geometry, one can see that, okay, if we draw a normal along the that means the normal would be aligned with the x-axis. It has the direction cosines. This capital X, which is the normal to the plane ABC, it has the direction cosines, say nx, ny, nz. Nx, ny, and nz. I think it is not visible. So here we write that okay, it is the nx, ny, nz. This is the unit vector, okay, which is aligned to capital X direction, okay, which is aligned to with the capital X direction. So with the help of this direction cosine, one can establish that okay, this implies this condition. If we rewrite, we get Tx of x minus sigma xx nx minus sigma xy ny minus sigma xz nz equals to 0. Okay, this multiplied with the area A B C equals to 0. Since ABC is different from 0, so we divide this expression with that. Okay. So basically the projection of ABC on xy plane is the area. Okay, this is the area projection of ABC. If you just provide a parallel ray of light, okay, and if you consider ABC as the opaque, then you get the shade, okay, shade, and that shaded area would be OCB. That's why you see that we are taking the nx, ny, and nz. In terms of that, we are writing down area OBA, area OAC, and area OCB, okay, as the nx times area ABC, ny times area ABC, and nz times area ABC respectively. Okay. So nx times that means this one, ny times this area means this one, nz times this area means this one. Okay. So we arrive at the first statement. Okay. So what we write? Let us write it. T x of x, T x of y, T x of z. So these are the components to be identified, and here sigma xx, sigma xy, sigma xz times nx, ny, and z. You see the first equation, this equation is written here. Tx equals to this times that plus this time this plus this time the last entry. Now if we consider the equilibrium equation along the y axis, that means this direction positive. What we get? We get y, and then if we first explain means negative explain means here, so xy, and then it becomes y, and then becomes yz. Okay. So you see changes here, xy, yz. So we write it down, sigma xy, sigma yy, sigma yz. Now you consider the equations of equilibrium, the translational equilibrium along z direction. What you get? You see this direction. You just first consider ABC plane, so along z direction you have z. Okay. Now you come to the negative x plane, sigma xz is acting, so you get sigma xz. You come to the negative y plane, that means here you see the downward direction yz is acting, so here you get yz. Now you come to the negative z plane, sigma zz is acting, so you get sigma zz. Okay. So here you see all the other entries, the form is remaining same, only these entries are taking different value. Okay. So using the similar argument, we can arrive at the last row, that means sigma xz, sigma yz, sigma zz. Okay. So with this we conclude that this relationship is valid whether it is a two-dimensional problem or three-dimensional problem, does not matter, it is valid everywhere. Okay. Now, one more point I would like to say, that this T traction vector. Okay. So, often we use the traction vector to identify or surface traction to identify the external forces. Okay. Suppose this is a body and this is the element on surface element, physical surface element on that body. So, on the physical surface element, you can apply the external force intensity, okay, external distributed force. Okay. So, that is a given quantity. Okay. So, that is a given quantity. In that case, when you consult with this equation, you see that the physical surface which is a given quantity, and over that you draw the unit normal, which is the intrinsic property of that surface, okay, geometric quantity, and this is also given. Okay. So, this is a given data, that means the external surface force is prescribed. In that case, what we see, that this stress tensor having these 6 entries, they adjust their value such that this equation is satisfied. Okay. But when, that means this is known and it has to adjust. When you go and you go to the interior and consult with any interior fictitious surface like that, here suppose we have cut this body into 2 parts. Okay. Here is the cut surface. So, here what we have seen, that we usually supply the statically equivalent force distribution or force in order to maintain the same equilibrium condition. So, in that case, this T surface traction is unknown. Okay. So, if you know the state of stress at a point on that surface, okay, then you can draw the normal outward unit normal on that surface, because you are cutting. So, you know the surface. Normal is the surface intrinsic property, so you can be computed once the surface expression is given. So, and if you know the state of stress at each and every point on that surface or any point where you are interested to evaluate the traction, what you do, you compute, you just take that stress tensor, multiply with the unit vector, entries with the outward unit normal, whatever value you get, that is the surface traction. Okay. So, with this I stop here. So, this part is over. Next we compute the tangent and normal components of this traction vector. Now, we see that, okay, tangent and normal components of this traction vector Tx. So, again we consider the right triangular wedge OBA, okay, that has some width, finite width, say it is B. Okay, where the hypotenuse AB, it becomes normal to the capital X axis. So, here we intentionally choose this axis to denote the normal direction, okay, and that makes theta angle with the small x axis. Okay. So, now earlier we have seen that, okay, this surface traction T, earlier we have resolved with respect to the small xy system, that means the Cartesian components. Now, there are alternatives. One of the choice may be you can resolve this T along the capital X direction. So, let us say that this magnitude of that magnitude of this would be the resolved component, that means the component of traction vector T along the capital X direction is T times the magnitude is sigma capital X times the unit vector n, where the unit vector n has the 2 components, 2 direction cosines, nx and ny. Okay, this is the direction cosine. So, entries are nx and ny, they are measured as cosine of theta, and ny is sine of theta. Now, with the help of that, what we can do, we can see, okay, how if we take the projection of this traction T along the capital X direction, it reads T x dot n, that we say that it is sigma x x. Okay, so that takes the following form: t x of x times nx plus t x of y times ny. Okay, so naturally means you can see that okay, it can further be expressed as okay. So this is the normal component. So that means normal component of this traction vector is represented as sigma x x, the magnitude, and n takes care of the direction. So this is the normal this can be t component of t x along x direction. Okay, so once we get the normal component, you can compute the shear part as minus so that means okay, this is the shear part. This we say that component. This is the tangential component. Okay, so this is the normal component and this is the tangential component. If you sum the take a vector sum of the normal component and tangential component, you get back the surface traction T. Okay, so that is acting on capital X plane. The same idea can be extended to three-dimensional situation. So we in 3D what we get, that we need to add one more component T capital X Z in Z, and here this may not be possible. Okay, so we get one more component T x Z minus sigma x x and Z. Okay, for 3D. This is for 3D. Okay, 3D you have three components. Basically, they are vectors. Okay, magnitude of that, magnitude of the normal component, that is this is the magnitude. Of normal component, and the tangential component, the magnitude would be how much? How much is the tangential component? That is you say sigma x s, say the tangential, or xt. Okay, that would be for 3D this one. Okay, so this is very simple. So when in the questions when we will be solving, I will be identifying the tangential component and the normal component. You can either follow this rule, this way of computing the tangential component, or since we have resolved this traction vector into two orthogonal components, one is the normal direction, that means along the capital X direction, and another is the tangential direction. So you can use the Pythagoras theorem, which says that okay, magnitude of T. So magnitude of T of T, this is this takes T capital X, x square of that, T capital X, y square of that, plus T capital X, z square of that. This is the magnitude of the traction vector. Okay. So we say that okay, so this tangential component that can be written as the T x square of that minus sigma xx square root of that. So you have two options. Either you can choose this one, component wise you just deduct, subtract the normal contribution, and then you take the Euclidean norm, or otherwise you compute the magnitude, square it, and deduct this one, this magnitude, and then take a square root. This is basically application of Pythagoras theorem. Now we shall see, okay, with this the Cauchy's relation for the stresses and the tangent and normal component of the surface traction, that part is over. Now we shall move and we shall utilize this concept in deriving the stress transformation for two-dimensional situation.